So let's then go on and look at what is required for maximizing total welfare. So basically the approach that we're going to take here is to first figure out what we would like to be occurring. So we know that if there's a monopolist who only cares about profit, well, this monopolist is going to invest whenever price hits this price threshold PM that you computed before. So I call this PM with the M for monopolist. And now we're asking, suppose we are a regulator who does not care just about profits, but cares about maximizing total welfare. So welfare including the consumer surplus. Then the question would be, for such a player, what would the threshold price be, PW, that instead maximizes total welfare? So that will again assume that we are not just looking at profits, but we are also looking at total surplus. So that's the first question. So what's PW? So presumably that's going to be a little bit lower, but how much lower? So you're going to invest a bit earlier than a monopolist. Then the next question is, well, suppose we are going to implement a price cap. So we're going to tell a monopolist, well, you do whatever you want in terms of investment, but the price that you can charge at any time is not going to exceed, cannot exceed a certain maximum price, which is the price cap. And then we'll figure out, if that's the investment problem now for the monopolist, so you cannot just set any price, but you can only set a price up to some maximum price cap. Well, what in that case will your investment behavior be? And then thirdly, we'll ask, well, now we're going to set the price cap, so we know from the second step what that means in terms of investment behavior by the monopolist. So how close can we get to making this monopolist under this price cap behave as though it were maximizing total welfare? So in particular, can we make sure that this monopolist that's exposed to this price cap, that is actually going to behave as if it's maximizing total welfare, investing as soon as the price reaches this welfare maximizing rather than the monopoly profits or maximizing price PW. So in order to start this first step, so what would be the price at which we should invest if our aim is to maximize welfare rather than maximize profits? Well, we have to make sure that we know what welfare is, the flow of welfare. So we knew what the flow of profits was, that was P times Q, right? Where P is given by this expression here, theta times Q to the minus gamma. So now we're interested not in P, but in the total welfare. So what's total welfare? Well, it's the total surplus, is the area essentially below this curve. So it's a red area in this graph, because remember, whenever we are not investing in capacity, the total marginal cost of producing is actually zero. So the marginal cost line here would be just the line C equals 0. So the area in between demand and marginal cost is the total red area here, where the red area would stop. And this point will be the point at which Q equals K actually. So for particular K, total surplus would be the total red area up to Q equals K, which is this point over here. So let's try to figure out first of all what this red area, what this size is. So that essentially requires us to find the area, find this red area, and we do that of course by computing the integral under this for this function, for this demand function. That's the area under the function. And then we'll again write down the Bellman equation, of course, but now the Bellman equation where the flow of profits is replaced by the flow of that surplus that we will then have computed. And then we'll go to maximize and figure out, at what threshold price should we now make the investments in order to maximize that flow of surplus rather than the flow of profits. So let's do that on the paper. So first step is, so what is given K, capacity that we have today, what's the flow of surplus. So the surplus in total, of course, is given by this integral, this red area. So the integral between 0 and K, so Q, the total quantity ranging between 0 and K, we're integrating this demand function. So this demand function was given by theta times Q to the power minus gamma, and we're integrating over Q. So this is the area of the red area basically in the graph. So it's the integral between 0 and K of the demand function. So let's do that integration. So what's the indefinite integral of this function of Q? Well, what do you do when you want to have a power function? You want to find the indefinite integral. Essentially what you do is you raise the power by 1. So it's Q to the minus gamma is going to be Q to the 1 minus gamma, and we divide by that 1 minus gamma. So why is this again the indefinite integral? Well, if I take the Q derivative of this thing, well, what's going to happen is this 1 minus gamma is going to come down, it's going to cancel against the 1 minus gamma that sits in the denominator here, and the power is going to go down by 1, resulting in minus gamma. So then we get back basically this function of Q over here. So this indeed is the indefinite integral, and we need to evaluate the definite integral between 0 and K. So right, it's like that. So what is this? Well, I have to just plug in K and then take the same expression that plugged in 0 and subtract that. So plugging in K would give me theta times K to the minus gamma divided by 1 minus gamma, minus, if I plug in 0 here, of course, 0 to the 1 minus gamma, or gamma was a number between 0 and 1. So this 1 minus gamma is going to be a positive power. So this is just going to be 0. So the answer here is just theta times K to the 1 minus gamma divided by 1 minus gamma. So that's the flow of total surplus. So now we need to solve the Bellman equation here. So the Bellman equation says we have a W now, which is the flow of total surplus at some capacity K and demand size theta. The Bellman equation says R times that total value, the total welfare value, is going to equal, well, the flow of welfare, which is, we just computed that, this expression, plus, well, then again, the familiar terms, theta derivative over here, plus a half sigma squared theta squared times the second derivative with respect to theta. So this is the Bellman equation, and we know, of course, again, what's the general solution here. So the general solution of this object is going to be, well, this first thing is the flow. So we first get the essentially the total surplus, but now integrated over time. So perpetuity of total surplus at capacity, fixed capacity K. It's theta is the stochastic process here, so it's proportional to theta. So this is actually a growing perpetuity. So that value is going to be precisely this thing. That's R minus mu, because we have this growing perpetuity, because it has this theta to the power 1 in the numerator. And then furthermore, we'll have an A K theta to the power beta 1. And we might have, of course, also a theta, a BK, if you wish, times theta to the power beta 2, negative power. But we're just going to leave that out because we want this welfare to be well defined even as theta goes down to 0, which is inside the domain where this weighting value is again going to be to be a valid function. So now we need to worry about the boundary condition. So we took care about the boundary condition at theta equals 0, but the other boundary condition is the boundary at which we're going to invest, which is going to be theta star. So at that boundary, so at theta star, or let me call that perhaps, let me perhaps call it theta w, right? Theta w, the welfare maximizing theta star, if you wish, the boundary at which we're going to invest if we want to maximize total welfare. So what will I have there? So given k, actually, what we have there is value matching. So the value matching condition, again using Pindike's results, the WDK equals I, so the marginal value of investing an additional unit of capacity should equal the marginal cost of investing, which is still I, and the smooth pasting condition here is going to be d square dk d theta equals 0. So this is for optimality, and these things should work actually at theta equals theta w. Theta equals, so they should be evaluated at theta equals theta w. So let's use the explicit expression that we have for this w here to figure those out. So value matching will then reduce to, if we take the k derivative over here, so we have the 1 minus gamma, which is going to cancel again this 1 minus gamma in the denominator here. So the first one gives me theta times k to the minus gamma divided by theta. I'm going to evaluate at theta equals theta w, so let me just write that already there. So at the boundary value, this 1 minus gamma is coming down, it's cancelled against this 1 minus gamma, so the remaining bit here is this r minus mu bit. And then of course here we also take the k derivative, so that's plus a prime k equals I, and smooth pasting is the theta derivative. So we'll also take the theta derivative on top of the k derivative. Of course, for this first term, it's just the theta that's going to vanish here. So we get k to the minus gamma divided by r minus mu. And for the second term, this beta 1 is coming down. So beta 1 times a prime k times theta w, beta 1 minus 1 equals 0. And now, of course, I'm again going to multiply this thing by beta 1 and this thing by theta w. So let me just do that immediately. So beta 1 over here, beta 1 over here, and beta 1 over here. Multiplying by theta w here gives me theta w here, and the theta w here, so it's going to cancel this minus 1. So now we are in business because these terms are the same, so we can cancel those. So what we find actually is subtracting these two equations is beta 1 minus 1 times our theta w that we would like to know divided by r minus mu is equal to beta 1 times I, or in other words, theta w times k to the minus gamma is going to be equal to beta 1 divided by beta 1 minus 1 times r minus mu times k. And this thing, so this thing is actually, times I, of course. So this right-hand side, you notice here, is independent of k, actually. So what we see is, this theta w itself is dependent on k, but theta w times k to the power minus gamma, that's a constant thing. So, and fortunately, again, this has the interpretation that we know, because this is going to be our PW. So it's the price level at which we should make the investment. So as soon as the price hits that price level, we should make the investment if we are to maximize total welfare rather than total profits. So let's then have a look at the slides again. So here's the slide that we were. So welfare maximization again means maximizing total welfare here. So we first calculated the total surplus, so that was this particular integral. Then we wrote down the Bellman equation right here. We figured out what's the solution to that thing. Well, that's the expected welfare if we keep k constant forever. So that's this growing perpetuity again. And this green thing here over here is again the option value that we have of expanding capacity in the future. We wrote down the boundary conditions at the investment threshold theta that I just called theta W, value matching and smooth pacing, and then I computed again indeed the PW here, which should be beta 1 I suppose, beta 1 divided by beta 1 minus 1 times r minus mu times I. That's the price level at which we should make this incremental investment. So before, we have Van Dijk's model essentially, and then the recap today, we computed what's the monopolist's price level at which it should make its investment. It's almost the same thing actually, but it differs just by this single red factor over here. So what is this red factor? It's 1 divided by 1 minus gamma. So remembering gamma being a number between 0 and 1. This red factor here is actually a thing which is bigger than 1. So this still tells us that the price level at which a monopolist would make the new investment is going to be bigger than the price level at which the welfare maximizing regulator would prefer to have this new investment made. So indeed, a monopolist is going to wait longer actually than is socially optimal in investing in new capacity. So that's the benchmark essentially. That's a benchmark of that we get if you want to maximize total welfare. We should make sure that there's this new investments coming up as soon as we reach this state as such that prices reach this PW level. So now let's look whether we can actually induce this monopolist to make such investments by imposing a price cap on them.